then share my screen and coming over here. So yes, welcome to our big data class for today. A couple announcements. Homework correctly due date due tomorrow. And there's a GitHub issue posted about the homework away Zoom thing right here, where depending on which version of the load tweets.sh file that you were using for the homework, you might have had an error uploading it to GitHub Actions. In particular, I think in the video, I had a file that looked something like this, specifically using bash features, specifically this time around the for loops like this. And this has to be run with bash because this is not a POSIX thing. This is a bash only thing, the ability to time a for loop. And in the GitHub Actions test case, I have it using the a POSIX shell right here instead of bash. So you are either welcome to edit the POSIX or edit the test case here to change this sh to bash and then use the script as is, or you're welcome to edit the script so that it's not using this time feature right here. The version of the script that's actually on GitHub, though, is POSIX compliant. It has the time around individual commands. So if you were using this script, then it's not a problem. But so if that's a problem for you, then easiest fix, change sh to bash, and that's fine. It's fine to modify the test case that way. After, so yeah, this homework is due Tuesday, tomorrow. After that, Wednesday, we'll go over in class the next and last homework assignment for the class. And this week, we'll finish up all the stuff needed for the final exam. So for the next homework, you'll have 1 week to complete it. And then after that homework's done, I'll post the final exam, and then you'll complete the final exam on your own. Any questions about anything administrative, timeline-wise, things like that related to the class? Yes.
What day is the final exam?
Question is, what day is the final exam going to be on? And it will be posted sometime next week at the end of the week, and you'll have at least a full week to work on it. So, yeah. I don't have a concrete day in mind. If people have suggestions, I'm welcome to take them, but probably like Thursday or Friday, post it next week. Again, so the format of the final exam, there's lots of practice versions of the final posted. We've been going over this one from the class with this final practice problems. With these sort of free response things, we'll continue going over this today. But this is historically, grades on the final exam have been much worse than the grades on the midterm exam because the midterm, roughly easy to check your work with Postgres. Here, there's last time in class, we covered some ways to sort of use Postgres to guide you through the process, but there's no like just simple one command to run to check your work on this. You really have to understand the details and get your answer based on that understanding. Good question. Any other questions? Another announcement, last time people were talking about extra credit in the class, so I just posted another extra credit opportunity here, a game called Deadlock Empire. It's not related to SQL or Python at all. It's in C#, but the particular things that you have to work through is still related to locking and deadlocks. So I figure it's good enough for extra credit for that reason. Getting if you can solve these problems, then the SQL Python problems will be pretty much trivial. These problems much harder. And so So here's the format of the game. There's instructions. If you get down to this locks section here, complete these levels, then 1 point, and then each subsequent section after that, 1 point. So up to 5 points total. I've used this before, posted it for extra credit. Never had anybody take me up on it, but you're welcome to take me up on it if you would like some extra credit. Any questions about that?
Well, as long as it kind of
Mhm. Yeah, so there's the 2 caveat tasks that you'll need for this class. And reminder about those caveat tasks. So clicking here and then clicking on the caveat tasks, the 2 details here for the culture. The way to submit this task is there is a GitHub issue to post to, and there's no Sakai link for this one here. You just post your response to this GitHub issue and you'll get the credit for that. The other one is the type speed task, that one. And for this one, there is a Sakai submission, and way down at the bottom, you run this command, and the output of this command is what you submit to Sakai, and that'll get you the credit for that. Does that answer the question? Cool. Yes. This Deadlock Empire game here, you can just either show it to me in person or send me an email with a screenshot, and that'll be good, and I'll enter it. Any other questions before technical stuff today? Okay. We are on the topic 10 folder for class, the B trees and indexes. And we've covered a lot of stuff on the 4 table scanning methods. And we're down here on this sorting strategies. What will be, we should finish this whole rest of this README file today. Remind ourselves real quick of the table scanning methods. We're going to do problem 3 right here on the final practice problems. This is the in-class questions_in-class.pdf file that we're looking at. And here in problem number 3, we have a relatively simple SQL query right here. But what's different about this SQL query from things that we have seen before is that there is a function being applied to one of our columns right here. We have this function right here of lowercase username that we were searching over. And when we have a function like this, our corresponding index also has to have the function. The index has to be over whatever is to the left-hand side of the equal sign. Or if this was reversed, whatever's to the right-hand side. Whatever's on the equal sign on this operator that's not the value that we're plugging in over here. So the corresponding create table command would look something like, create index command, create index on users, and then inside of here, it's lower username like that. Totally okay to use arbitrary functions inside of your index over here. And then you can speed up this query. This currently we already have a very similar index to this that's created by the information in the tables above. We have an index that's created. What we already have is users username like this without the lower. This is what we already have. And Postgres has no, at least in its like index solving system, has no internal knowledge about what this function does. So Postgres does not try to take advantage of like the semantics of any of these functions over here. Does not use this function or try to interpret this function in any way. That you actually have to have, like, so for example, if all of the usernames were already lowercase, then this index up here and this index down here would have the exact same contents inside of it. But you would still need both of these two indexes to do this query. You would still need to create this index right here on the lower using the lower function in order to do this query. Even if the contents of these two indexes are exactly the same, the only way that Postgres knows to be able to use an index is if the contents, the thing that we're comparing against, exactly matches function names and column names. Any questions about that? An easy way to miss points on the final exam is if we consider a similar looking but very different query, where in the where clause, this similar query will look something like where, and then username. So this username is the column because it does not have the colon in front of it, equals, and then lower colon username over here. So the only difference between this green query and the original query up here is that I moved the lower function from the left-hand side of the equal sign to the right-hand side. That I moved the lower function from this position to this position over here. In this case, what's on the right-hand side is just a constant because it's got a colon in front of it here. This is something that the user has entered. And then Postgres instantly can just compute what is the lower version of that, what is the lowercase version of the text entered over here. And we only have to do that once. It's not something that we have to do for each row. And so then the column or the index that we need for a query with this kind of constraint would be create index on users username, because this column right here matches this column right here, the thing that's to the left of the equal sign or the thing that's on the side of the equal sign not containing the constant information that the user has entered for us is what's contained inside the parentheses over here. And in this case, this is an index that we already have created for us. It was created for us automatically because there's a unique index on the username column. So we actually don't need to create an index in this case. Already exists, don't need to create it. So it'll be, there'll definitely be something on the final exam that will require you to understand the difference between these two where conditions and the type of index that is created on them in order to speed up the queries. And so if you have questions, make sure to ask them about that. Does this make sense? See head nods? Okay. Then let's move on in. I'm in the README file right now, and we're at the sorting strategies. So there's lots of situations where we're going to want information sorted in our SQL query. The most obvious is if we're using an order by clause, but we'll also see later on in this in these notes here that there are other operations that require sorted data as input to them. But the most obvious reason for sorting things is the order by clause. And so let's see how Postgres does that. There's two basic strategies, and the first one is an explicit sort. And the explicit sort technically has three different types of explicit sort. The first type is that if your scan data fits into memory. So this is the working memory system parameter here. So 20 megabytes. So this is basically your entire table fits inside of 20 megabytes. And you have a limit in clause right here. Then Postgres will do what's called a top in heap sort. So this is something that you likely did not see in your data structures or algorithms class. But instead of an in login runtime, you get a runtime that's linear. So this lowercase n right here, again, is the total number of rows we have in the table. So it's linear in the total number of rows, but then it's log linear here in the size of your limit clause. So this is a little bit of a speed up that we can take advantage of the limit clause here for an explicit sort. Otherwise, if you don't have the limit clause, then we'll be using quicksort here, getting the standard in log in runtime in the average case. If things don't fit in your working memory, so if you have a large table that you're working with, then Postgres will use merge sort to implement things. And it has a special version of merge sort where all of the intermediate sorted tables end up getting saved to the hard drive. This is an extremely slow operation because it has to involve the hard drive. So definitely something that you want to avoid. But even these sorts up here, they're in memory, but they still have this linear dependence on the lowercase n. So it's still something that we would prefer to avoid if we can. The real thing that we want to do is avoid sorting algorithms completely. And we can again use indexes to avoid our sorting algorithms. And the B-tree index in particular allows us to do that. So recall coming over here to our Haber.com, our Russian Reddit website, this picture of the B-tree index, that down on the leaves, all the information is stored in sorted order. And the reason we have these little pointers between the leaf pages here is so that after we find one leaf node, we can just traverse in a sorted order and get everything sorted. So if we have an appropriate index, then we won't actually need to call an explicit sort at all. And so then the runtime is just however long it takes us to traverse the tree, so that logarithmic runtime. In a second, we'll go over to the example or the problems here and do some examples with that. But are there any questions on the high level idea of these sorting algorithms, sorting strategies? Okay, then let's come over to here and let's come take a look at problem number 4 here. So problem number 4 is asking us to create indexes so that we can use an index-only scan, avoid an explicit sort, and take advantage of the limit clause here for faster processing. In general, if we're using an index-only scan, one of the good things about the index-only scan is that we avoid the explicit sort because everything is stored in the index that we need, and the index is already sorted. So by using an index-only scan, we avoid the explicit sort automatically. Similar for the limit clause, the only table scanning strategy that cannot take advantage of the limit clause, the only table scanning strategy that does not take advantage of the limit clause is the hash, the hash scan. And the reason for that is because, again, we have to build up a hash table of the size of the entire table that we have. And so the hash size is omega of n over a. Again, n is the total number of rows, a is the number of data points per page. So this is the number of pages. N over a equals number of table pages or heap pages. Table pages and heap pages are synonyms for each other. And so no matter what our limit value is, we still have to build up something that takes up the entire size of the heap table. And so we don't really get any speed up based on the limit clause. But the fact that we're using an index-only scan, if we can construct an index that can use an index-only scan for this query over here, it means that we'll get the explicit sort and take advantage of the limit clause for free. So all we have to worry about is how can we use an index-only scan on this table over here. In this case, where did here we go. So what will look like is great index on, and then it's the users table. This down here to this line. And the first thing that we are needing inside of our index is always going to be what's inside the where clause over here. That we always have to satisfy our the rule for being able to do an index-only scan is the order of your columns over here. The leftmost things have to be any equality constraints that you're searching for. And then the very last thing is either an inequality constraint or the order by clause over here. In this case, there are no equality constraints over here. There's only the inequality constraint. And so I can put created at underscore at as my first column over here. That satisfied having this index on the created at over here satisfies this the where constraint right here. It means that we'll be able to find all of the things that are less than or equal to the created at efficiently. And then scanning those leaf pages of the index, everything will be returned in order by descending on the created at right here. In order to make this an index-only scan, though, I'll also have to include this ID users information up here. And I'll have to put that at the very end, ID underscore users like that, so that the information is still inside of the index. But it's in particular not to the left of created at because we're not using it inside of the where condition in anywhere. The limit 10 down here, we don't have to do anything special inside of our index to take advantage of that. We just have to make sure that we're able to use an index-only scan based on the columns mentioned and the conditions right here. I'm going to do one more variation of this, and then I'll stop for questions. The variation is what if. So in green down here, we'll have the what if. What if the where clause also had id underscore users equals a colon id underscore users followed by an and what we already have existing in the where clause up here. So followed by and created at less than or equal to colon created at. In this case, because we have the equals condition up here, this is a stricter condition than the less than or equals down here. So we have to satisfy this exactly before we can do the sorting, before we can find the things that are less than or equal to up here. And so my create index command would have the opposite column order. Create index on users id underscore users comma created underscore at, like that in this case. So again, the difference is that I have switched the order of the columns down here. And again, the order of the columns affects how the B-tree structure is created, which columns it's using to determine how the leaf nodes get splitted and ordered in the very bottom row of the B-tree table. And the rule again is that equality constraints have to be the most restrictive constraints always to the leftmost position in your column list, because those are the things that will get sorted on first inside of the B tree. Then you can have at most one inequality constraint. If you have an order by, something that you'll be sorting on, it has to match what you're doing the inequality constraint on here. So in this case, they both match, so that's okay. So following by the inequality constraints over here. In this first example up here, we had more columns up here that were not used anywhere in the where clause or the order by. And so after all of your conditions that you're creating for making the where clause and order by speed up, in order to go from the index scan to the index only scan, you have to have all the information in the index somewhere. And so whatever other columns you need due to the select columns up here, those come in the rightmost position. Here we're using a descending, order by descending. Turns out it doesn't matter whether you're ordering by descending or ascending. The index, how you create the index is exactly the same. You can actually modify the create index command so that on the hard drive things are arranged in a descending or ascending order, but that doesn't have any effect on performance because you can always just traverse the index forwards or backwards. A lot of things there that are all pretty abstract, but definitely going to be on the final exam. So definitely important to understand why the order of these two columns is different in these two cases, and understanding how you would generalize that to other select queries. Any questions about this problem? This all seem like 100% understood all of those subtleties, or yeah, a lot of head shaking. So I think it takes seeing a lot of examples of these different situations in order to understand them. And also just like working on them on your own before seeing the examples. So that's why there's a lot of the practice problems, and they all have full answer keys along with them, so you can see, try to complete it, see if you understood what was going on, and check against the answer and your understanding of it, or the explanation, to see if you understood it. And definitely do that before the final exam so that you'll be able to ask questions if things aren't lining up the way that you think they should. Any questions at this point, Bill? Too hard and abstract for questions? Okay. Let's see. Number 5 right here is on joins. We'll do this one here in a second, but first I want to skip down here to number 6. And the thing that number 6 does differently is it has this group by clause. So we're going to take a look next at the 2 different algorithms used by the group by clause and what we need to do to make indexes for this particular problem right here. So sorting strategies coming down. The next thing here is the aggregate strategies. Aggregate strategies, anytime you see a group by clause going on or an aggregate function anywhere like the count or the sum or the max. That's the indication that you'll need to think about the aggregate strategies. There are 2 aggregate strategies, the group aggregate and the hash aggregate. And this top link right here has a takes us to a slideshow that goes over the differences between these algorithms. So I'm going to take us to that slideshow and we will walk through what the algorithms are doing. We'll first talk about the group aggregate and then the hash aggregate here. Here, the group aggregate, the key important thing to understand about the group aggregate is that it requires data to be sorted on the columns or on the properties that you're grouping by. So here in this picture right here, what we're looking at, each one of these circles is a different row of data. And there are two columns in these rows. The first column is what color the row is, and the second column is what number is contained inside of the row. If you go backwards on the slide, so we're currently looking at slide 15. If you go backwards, it shows a handful of SQL commands and breaks them down for you about like, I don't know, background on how it's structuring these things. So if the problem setup doesn't fully make sense, starting the slideshow from the beginning would hopefully help with that. But the key thing here is these 10 or so data points, they have been sorted by their first column by their color, and the second column by the number. We're trying to add up all of these numbers together for each color. And in the group aggregate, if we already have things sorted this way, then what we can do is we just have a little state counter over here. And we'll start by counting up everything in the blue color. And so here it added together the 1 and the 2 right here to give us the 3 down here. It still has this 3 left to add up, and it's added up that 3 into this 6 over here. And as soon as it does that, it outputs the 6 as in blue as something that can be passed off to downstream processing as a final row. We know that things are already in sorted order over here, so we know that as soon as we get to the end of the blue things, we're never going to see another blue row, and so it can pass this off to a downstream process for processing. It started counting up the green state right here. It's done this first 1 and the 3, getting the state 4, and continues doing that, adding that 2 and that 2 as well to get the 8 over here, and that can immediately be sent off to downstream processing as well for whatever other tasks there are. And then it adds up all the red things 1 row at a time here, adding them together to get our 5 output down here. The hash aggregate does not require things to be in sorted order. So that's one advantage of the hash aggregate. You don't need things to be in sorted order. What we'll see though is that you're not going to be able to send things off to downstream processing 1 at a time. So here, as we take in these rows 1 at a time, it will add new, so it's just processed this 1 state right here, have this blue 1, and now it's going on to something green next, but it's still having to keep track of the blue things separately over here. And so it's processed that green 1, and keep going through processing things, adding up until we get to these last 3, adding things to the blue and the green and the red. And eventually, once we've processed everything all together, we'll have the final same results as the group aggregate, but we can't actually return those results until we've processed everything at once. Another downside to the hash aggregate about not being able to send off results to downstream tasks at once is that we have to store in memory all of these results at once. And so if there's a lot of different values on the column that we're grouping by here, a lot of different values of the column that we're aggregating by, then this table right here of intermediate results can grow very, very large and potentially not fit into memory anymore. So the hash aggregate can or will use more memory, potentially too much memory, because it has to store all of the information about all of the states throughout the entire process. Those advantages and disadvantages are summarized here in this last slide that we'll go over. And this is the one thing that you'll have to make sure that you understand to be able to answer the problems. That the group aggregate, again, requires sorted data, so that's the downside, but the advantage needs less memory because it can return things immediately, doesn't have to keep storing everything. The output that it returns remains sorted, it returns the data on the fly, and can do the counting distinct as well. The hash aggregate, the only advantage of the hash aggregate is that it accepts unsorted data as input. Everything else about the hash aggregate is a negative, sort of the opposite of the group aggregate, needs more memory, the return data is unsorted, and has to return the data only at the end, and so on. So in general, whenever we have an aggregate, we'll want to use the group aggregate ideally. And so we'll want to have a situation where we're passing sorted data in as input to whatever we're doing the group aggregate on. We'll go over here to the problems in the notes here in a second. But any questions at a high level idea of the group versus hash aggregate before we look at the problems? Okay. So problem number 6 right here. Let's first think about, well, so what 6a here is saying, create indexes so that the following query will run as efficiently as possible. So this is sort of the most generic form of a problem that I can ask. Is I'm not giving you any hints about making it an index-only scan or what sort of features here you can take advantage of. You'll have to figure out for yourself what features of this problem are things that you can take advantage of and make it fast. In this case, what we're going to see is that you're not going to be able to take advantage of either of these two lines right here, and we'll only be able to take advantage of the group by aspect right here, doing the group aggregates. So we'll start by creating our index that will take advantage of or make things sorted so that we can do our group aggregate, and then we'll talk about why we can't take advantage of the order by or the limit clause down here. So the group by here is we're grouping by tag. So we need things to be sorted by tag when they get as input to the grouping algorithm. And in order to do that, it'll be a create index on tweet tags, tweet underscore tags with tag as the input right here. When we do this, this index right here is not an index that previously existed. If we scrolled back to the top, we'd see there's no special unique constraint on this tag column right here. So this is an index that we would have to manually create, and that index will make the group by clause here happen faster. The next thing that we might try to speed up is this order by clause right here. And in order to try to speed up the order clause, so I'm going to write something in green right here that we would like to be able to do, but we can't do. We would like to do this, but we can't do this. And that would be create index on tweet underscore tags of tag comma count star, like this. The key reason why we can't create this index, well, maybe before the reason why we can't create this index, the reason why we might like to create this index is because if we had this right here, then we'd be able to do this order by on the count without doing an explicit sort anywhere. That the output of our group by operation would come out in sorted order. But in this case, this count operation right here, this is an aggregate function. And aggregate functions cannot appear inside of a create index statement. Aggregate functions can't appear inside an index. So previously we created an index that used that lower function. The lower function is something that happens only on like an individual value at a time. And so that can go inside of an index. Aggregate functions cannot go inside of an index. The technical reason for this is because indexes don't store any of the information about the multi-version concurrency control information. And so there's no way to we could count, for example, how many rows are actually contained in the index, but we don't know whether those rows are visible or not visible without going back to the table. And there are people trying to work on this. It's probably something that will be implemented, I don't know, in the next 5 years or so in Postgres, but there's sort of minor technical obstacles in the way of doing this right now. So we can't implement the order by up here. We're going to have to do an explicit sort. Part B down here, given the indexes created above, is the limit clause likely to significantly speed up the query? Explain why or why not. The answer is that given this limit clause up above, the best that we'll be able to do is an explicit sort. We must do an explicit sort. Must do explicit sort. And the algorithm that we'll use here for the explicit sort is that top in heap sort. And that'll have runtime again of theta in plus uppercase n log n, where the lowercase n is the number of rows in the table. And the uppercase n is the amount that we're limiting by. I'll say that as just, it's the result of a limit in clause. This n up here corresponds to this n right here that we're doing the limit on. And so this explains sort of the why or why not, what the final speedup is going to be. To actually answer the question here of significantly speed up, to my mind, a theta in operation here is not significantly sped up compared to in log n. This doesn't seem significantly sped up. This doesn't seem significantly, underlining the significantly, faster than theta in log n of quicksort. To me, to my mind, significantly faster is like a logarithmic improvement going from n down to log n. And so I would say the answer is no. But if you were of the opinion that going from n log n to n plus uppercase log n did constitute significant, and so you said the answer was yes, and explained the same exact thing here, that would also be a full credit answer. For a lot of these problems like this, there's going to be, the question will be sort of maybe phrased as like a yes/no sort of Boolean question here, but the real meat of the grading and the work that you'll have to do in your explanation is in the explain why and why not. And as long as the explain why not hits this correct feature about doing the explicit sort here and the algorithm of the top in heap sort, then it'll be full credit no matter what your final conclusion is. Any questions about that? Yeah, Sophia. So your question is, what if this group by wasn't here? How would that change things? The answer is that if the group by right here, if that's not there, then this tag up here would also not be here. And so our final query would just be select count star. This is always going to have exactly one row in its output. And so the order by here, it won't give us an error message, but there's always just going to be one row. So this is sort of a meaningless thing. And similarly, the limit 10 clause down here is also meaningless. If we're just getting one row, limit 10 never helps us. And if we're doing a count star, then the only way to implement this is by a sequential search over the table, counting how many rows there are. So there's no way an index could speed up that particular query. So the question is, why would this not be a valid SQL statement right here with the tag right in the select columns up here, but no group by down here? The answer is that by definition, according to the SQL standard, anytime you have a aggregate function in your select query, any other columns that are not that aggregate function must be in the group by down here. And otherwise, it's a malformed SQL command. Postgres adheres to this SQL standard thing religiously, and so requires that you have this group by clause down here with the tag not being here. Other databases are less picky about the SQL standard, and so MySQL, for example, does not require you to write this group by clause down here, and you could just have this tag clause up here. Under MySQL, though, this query right here is 100% equivalent to the query without the, where did it go? This query right here is 100% equivalent to this query right here under MySQL. That somehow we still have to group by all of the tag columns together to count how many times each tag appears, and whether we include this explicit part of the SQL here telling us that we're grouping by the tag or not, the SQL engine still has to group by the tag somehow in order to do the count over here. Did that answer the question? So the question now is, let's say, what if the query was select count tag like this? In this case, the best thing that we can do is still scanning over the entire table, because ideally what we would like to have for a situation like this would be to do an index only scan where the information in this column right here appears in the index, but because this is an aggregate function, it can't be contained inside the index itself. And so it has to actually scan the table and actually count all the individual rows. This is the sort of query right here. This is a query that seems like it should be able to happen fast, and seems like you should be able to speed it up with an index. But it is impossible to speed this up with an index. A query like this, where you have select in an aggregate function, this will always take omega of n over a time. Again, where n over a is the total number of pages inside the heap table. N over a equals pages in heap table. One of the, so this is actually a very common type of query to want to run in practice, doing a count like this. If you, for example, are Instagram and you want to show how many times people have upvoted a post, this corresponds to a query like this, where you have a table where there's updates, and you have a count star in order to display that. And there's not, at this point, an easy way to make that fast in Postgres. Over the, I'm going to post a handful of videos for you to watch in about a week. One of those videos is by the head of engineering at Instagram about how they, like the details of queries, what they do to Postgres to make a query that looks just like this run fast. and how they actually implement the counting how many upvotes an Instagram post has. But it's a non-trivial thing to do. So another maybe takeaway highlight is that if you're running a web page, implementing a web page, and you have queries that have aggregate functions inside of it, that as like a CTO level person, that is something that would be scaring you about this query is likely to cause the web page to go down from taking too long at some point, because there's no way to speed this up without doing a whole lot of weird stuff. Good question. Any other questions about this so far? Okay, we will go on to our join strategies next then. And after talking about them at a high level, we'll come back here to problem 5 and to take a look at how to solve problem 5 here with these join conditions. Scrolling down here. So join strategies, these are used anytime you have a join, no matter what the type of join is. So cross, inner, left, outer, full joins. These are the algorithms, the strategies used for implementing those in practice. Historically, and by historically, I mean like 2014, joins are traditionally thought of as being like very slow operations. Currently in modern databases, it's these aggregate functions that are the only like actual slow operations, and joins are not particularly slow right now, as long as you have appropriately created indexes. But one of the things that led to the rise of NoSQL databases, like so MongoDB, Cassandra, one of the features of these databases is that they explicitly do not support joins, and they don't want to support joins because they want people to write their SQL queries that don't use joins, so that everything will sort of automatically be fast without the programmer having to think about how to create indexes and a special way to make joins fast. But we'll be covering this, the strategies of how to make your joins fast so that you can have the denormalized or the normalized database, whichever you would prefer, and get the, we'll see that with the right indexes, your normalized database will be at least as fast as the denormalized database. This reference right here goes into all of the details, but we'll be staying in the notes here, talking about the algorithms. At a high level, there are 3 types of join strategies. This first one here, the nested loop join, is sort of the most obvious algorithm to use, and it's something that works in all scenarios. And in particular, you do not need an index to use the nested loop join. The pseudocode of it looks like that if you have 2 tables that we're trying to join together, so this table A and this table B here, you loop through everything in A, and then it's just, this is why it's called a nested loop, everything in A, then loop inside of B for everything in A, adding this join condition right here. So these 2 for loops right here get us the cross join by itself, and then this condition right here handles whatever the condition that's making it an inner join or an outer join or left, right, full outer join. The overall runtime here is O of m in here, where m is the number, the size of the A table, and in is the size of the B table. So quadratic runtime using the nested loop join without indexes. Quadratic, very bad. So this is the main thing that gives joins its reputation for slowness. Any questions so far? This second variant right here, if we do have an index on the inner table that we're looping over, sometimes this is just called the nested loop join with an index as its own separate join strategy. So sometimes people talk about 4 join strategies, but I think it's it's easiest to understand it as just a special case of the nested loop join here. And what we'll do if we have an index on the inner table right here is we'll just replace this loop right here with this if condition with a access to the index, and doing either an index only or an index or a bitmap scan to get all of the rows that would be satisfied, that would be output by these 3 lines right here. So this find rows B and B satisfying the join condition right here. We would do this using our index with the logarithmic time access right here, outputting each row as we find it from the index. The runtime here being a theta m times log n runtime. So a significant speed up going from quadratic down to the log linear runtime. One of the nice things about joins is that they're commutative. So whether we do the A first and then the B, or the B first and then the A, doesn't matter. And so whether we have an index on B or an index on A, we can still speed up the join. And so this right here just saying that the order of the join doesn't matter from A join B, same as from B join A. And now we can use the index on the A table here, swapping the runtimes down here to theta n log m instead of theta m log n. If one of our tables is relatively small, then this outer factor right here doesn't matter, and we get logarithmic runtime. And so if we have a small table that we're joining on, this is the nested merge join with an index is the best that we can do. A very common way to have a small table like that is by having a limit clause that just limits how many rows that you can consider from one table. Any questions on the nested loop join at all? The hash join is, in practice, the join that Postgres picks the most often. And the main condition that's required for the hash join is that you have an equality constraint condition, an equality condition in your join. That's the most common type of condition. And so hash join very often used. You also don't need an index for the hash join. So if you're joining and you don't have indexes, hash joins probably the thing that's going to happen. The pseudocode, what this looks like, so it builds up a hash table for the join column on B, basically building up its own small index that will be used just for the purposes of the join, and then doing a the hash index traversal on the inner loop down here. The runtime of this is pretty good. We get down to a linear runtime instead of, so linear in both m and in, but we have a very large overhead because of having to create this this hash table for the two tables. The hash join also not able to appreciably take advantage of the limit k clause. The merge join is the one that we're going to always be mostly be targeting with our indexes. The nested loop with an index is good if the outer table over here has a very small number of rows inside of it. But the merge join is always good no matter what how large our tables are. And so the merge join is the type of join that we're trying to cause to have happen when we're creating our indexes. And the idea of it, it's basically like the merge step in a merge sort. So it requires sorted inputs from both of our input tables. Typically, this will happen because we were able to use an index or an index-only scan to get the information out of those tables, and then also an equality join condition. This thing right here, we don't have control over, but almost always satisfied. This condition up here, getting the sorted inputs, this is what we'll be creating our indexes on in order to force the inputs to be sorted. If the data is already sorted coming in, there's no setup overhead. Otherwise, you'll have to run that sort step explicitly. It's also really easy to stop early and take advantage of the limit clause. The pseudocode of the join here looks like this. This is just the merge step of the merge sort algorithm. So we have two indexes right here, one corresponding to each of the tables, and just looping over those two tables. If we're satisfying the join condition, then output the thing that satisfied them. The runtime over here is linear in both im and in, very small overhead here. And if we do have a limit clause k, then the runtime becomes theta k, because all of these loops will stop early up here. So again, this is the best case scenario for joins. And when you're creating indexes, this is what you'll try to achieve. Any questions about the merge join or the any of the sorting strategies? Okay, we will take a look at the problem here in a second. I just want to talk a little bit about the join order first. It turns out that the order that you join tables in is extremely important in the runtimes. The join strategies that we talked about above are only considering two tables at a time, but in general, you can join an arbitrary number of tables together. You saw in the Postgres, sorry, not the Postgres, the Pagilla assignment, that you had to sometimes join 10 or 20 tables together to solve a problem. And when you join multiple tables, you'll always use parentheses to group tables, or Postgres sort of groups those tables into pairwise join operations, joining things two tables at a time. It turns out the optimal way to join those tables together is an NP-hard problem. It's a very famous NP-hard problem, so not computationally possible to solve that. And but Postgres has a number of good heuristics in its query planner to try to pick the best way to join things together. And you don't have to know anything about these the algorithms for selecting the optimal join order for this class. In this class, you only have to know the strategies for joining two tables at a time. Okay, so let's jump over here to problem number 5, and let's think about how can we optimally solve this problem. In particular, it's actually a question. Yes.
Like the join and like the winner like tweets, whatever color those tweets are. If you submit one of them, if you sugar
So a join clause here is syntactic sugar for, well, so this join right here is an inner join. An inner join is syntactic sugar for a cross join plus a where clause. So this could be rewritten as two cross joins plus more conditions down here in the where clause. Good question. The question is, does the way that we write the queries out here affect how Postgres is able to determine which merge strategies, which join strategies to use? The answer is Postgres is very good at understanding the different types of syntactic sugar and ways of rewriting problems, and that Japanese textbook goes on into gory details about what the different syntactic sugars Postgres finds equivalent from a query planning perspective. But basically, unless you're really going out of your way to break Postgres with things we haven't talked about in this class, it will understand all the different types of ways of writing the different joins. So whether you're writing your join as a cross join plus a where clause, or an inner join like this, or if you're using an outer join, if it'll be able to figure things out for you. Actually, from the things that we've seen, the main way it might not what we talked about before was that the left join or the right join, any of these outer joins, those are equivalent to an inner join with a union on a the not in operator, the not in some sort of query like this. This subquery like this, subqueries are generally less efficient than using the join operator. Subqueries generally less efficient. It's very hard to convince Postgres to use a join strategy if you're using a subquery like this. And so that's one of the reasons why the general preference is that if it's possible to write something as an outer join, if it's possible to write a subquery as an outer join, people will prefer to write it as an outer join because it enables more optimizations in Postgres. Did that answer your question? Good question. Okay, so let's start by considering or recall that we have these join operations here, and we want to make them as fast as possible. So we want them to use the merge join strategy. And we'll start thinking about this in terms of without the where or the group by or the aggregates. So we'll start by thinking about a simpler problem that, I'll write it like this, does not have that line, does not have that line, and the select up here does not have the aggregate. So it's only joining without using any of the these other features. And then after we have thought about how to make the join fast, then we'll think about adding these other features. So in order to use the merge join, the key idea here was that we need to have our inputs to the join operation be sorted. So here, if we first consider this join operation up here, maybe we were thinking about putting parentheses like this, joining the users and the tweets table using the id users column. What we would need, I'll call this the first join here. In order to make join 1 happen, we need 2 indexes. Well, in order to make join 1 happen using the merge join strategy, we need 2 indexes. The first on the users table, create index on users, id users like this. And the second, create index on tweets, because that's what we're joining against. Tweets, id users like that. And if we do this, then both of these, the inputs to this join operation right here would be sorted. Then we would have to, the next join that we would be doing is combining the results of this first join with this second join down here. And I'll call that the second join operation. I'll do that in red. This is this join here being joined with the results of the orange join right here. If we do that, we'll need to have the tweet tags here come out in sorted order. So join 2 right here. Create index on, oops, yeah, tweet underscore tags id underscore tweets like that. We'll make the tweets from this rightmost table come out in sorted order. The question though is, how do I make the tweets in this left table inside these orange parentheses right here? How do I make those come out in sorted order along the id tweets column right here? It's a difficult thing to do because we have the id users up here. We're already getting things coming out in sorted order on id users. So here we'll be able to use the merge join on the orange join, but there's not going to be a realistic way to use the merge join to combine the orange together with the red right here. Instead, combining the orange with the red would have to use the nested loop join with an index on the right table right here. I'll write this out. This here can use the merge, and the red down here would have to use the nested loop. This is one possibility if we parenthesized things like this, where where we're first doing the leftmost join and then doing the rightmost join. Another possibility is that we could parenthesize things the other way, do the rightmost join first, and then do the leftmost join. In that case, our indexes, we would first do this in green right here, doing the rightmost join first. So now the green one here is our join one. And create the index on, we'd still have this red index down here on id tweets. Tweet underscore tags id tweets like that. Now on my leftmost table here, tweets joining with tweet tags, my index on tweets, create index on tweets will be on the id tweets field in order to facilitate a join with the tweet tags as the first join table that we do. This here would result in a merge join because we get both of these two things here in sorted order. And now we would take that joined table on the right and join that to the users table on the left. So in blue over here, the blue being the join 2. Here, this leftmost join is on id users, and so the join 2 right here is create index on users, and then it's the id users column that's being joined. Id underscore users column that's being joined. In this case, you can see, so Postgres would be deciding based on its own internal heuristics which one of these parenthesizations is going to be most efficient. Even if you add parentheses, so it's valid in SQL syntax to add parentheses. All of these parentheses I've added up here would be valid, would not change the semantics of your code in any way. But Postgres would just ignore those parentheses and do its own thing to decide which order to join things together in. So in order to give Postgres the most flexibility possible, you would want to create all 6 of these indexes here, but then also notice that some of these are repeats of each other. So like the create index on users id users appears in both spots, and the create index on tweet tags id tweets appears in both spots. It's only the table in the middle here that we have to create 2 sets of indexes for, one for doing the join on the left table first, one for doing the join on the right table first. The joins on the outer tables have the same set of indexes no matter which join order we're doing. So this is a super complicated problem. We've only talked about the joins. We haven't even talked about the rest of this problem, what's going into it yet. We'll finish that up on Wednesday. There's a good stopping point for us for today. If anybody has questions about this, then yeah, I'm happy to take those after class here, have office hours now, happy to talk about homeworks as well. But I would recommend before Wednesday's class to make sure that you have review this material a little bit, because as much as today's material was so much more and in-depth and potentially confusing as last week's material, Wednesday's new material will be even more of that, based on building on things than today's material. And so if you don't have a good grasp of today's stuff before Wednesday, you'll be really lost on Wednesday. So that's it for today. And